Okay, class, today we're going to look at the first method, which I've selected that is going to help you to determine the highest or lowest point, also called maximum or minimum, for a quadratic function. It's very useful. Practical applications are limitless when we're working with a system that can be modeled by a quadratic function. We want to find the optimum value, which we would call for maximum and minimum values. It's an optimum. I'm going to focus on this question right here a fair bit in the lesson. What is the equation of the axis of symmetry of a parabola? Okay, and the method of partial factoring uses the axis of symmetry. Okay, completing the square we will get to, and it's a little bit more of a technical algebraic method, but partial factoring is quite simple mechanically to do, but the concept is a little bit more difficult to understand. So let's look at the Investigate B on page 27 to start. So we're instructed to graph the function as shown, and we're answering some questions based on it. Well, to graph this, we have some options which we could, employ. We could set up a table of values. I would suggest here that if you were to factor it, because 2x is a common factor to both terms, what we can do is factor out 2x and produce two factors, which now allow us to determine the zeros, or also called the x-intercepts. Okay, the x-intercepts are easy points to use because they are symmetry points. Okay, they're on opposite side of the axis of symmetry, and in this case, the y value, also the function value, would be 0 when either, and it can't happen at the same time, so we say either or, either 2x equals 0 and x equals 0 would satisfy that, or x plus 2 equals 0 and x equals negative 2 would satisfy that. Okay, so these are our two zeros. Okay, they are the points where y, or the function value, is 0. So we could plot those on a coordinate grid, 0 and negative 2. Put our 2 points right here, and put a little scale on this, label my axis, and all right, so that's part of it. Now, when it asks us to find the number of x-intercepts, we've already solved that. There are 2. Using the x-intercepts to find the vertex of the parabola. Well, when we plot the x-intercepts, we do know that the x-intercepts are at the same vertical level, which means they're symmetry points, and that tells us that the axis of symmetry passes right in between them. It's the midpoint. So what we do know now is that y for the vertex corresponds to x equals negative 1. Okay, so x equals negative 1 would actually be the axis of symmetry equation. Okay, and the axis of symmetry is a line, and it's a vertical line, and vertical lines have an equation in the form x equals a constant. So this is the axis of symmetry equation, which really tells us that the vertex, I'll call it v, has an x-coordinate negative 1, and the y-coordinate is simply the function value at negative 1. So we've quite quickly determined the vertex by just finding 2 symmetry points. Okay, now here we would have to go back to the function equation and substitute in negative 1 for x, and it was 2 times x squared plus 4 times x, or we could use the factored form, which was 2x times x plus 2. Either way, we're going to get 2 subtract 4, which is negative 2. So our function value at negative 1 is y equals negative 2. So our vertex now is known to be negative 1 comma negative 2. So we could plot that on the graph. Negative 1, negative 2, and there's our vertex. Now, knowing that parabola here has symmetry, it would have to open upward. From there, we could give a quick sketch of the graph and label that with our function equation. Okay, so factoring can be very useful in determining the vertex, which in this case would be a minimum, obviously. Okay, the leading coefficient in our function equation is a positive number. Okay, now we direct our attention to question number 4. In this Investigate B, page 27, we're looking at two different functions which are related. Okay, this would be part of a family of functions that share the same vertex. This function here has been translated 2 units up from f of x, which is this. Okay, and the same function is embedded into h of x, having been translated 5 units up. So if we were to go back to the graph and imagine moving the entire function 2 units up, then we would have, in the case of g of x, we just have the vertex now at -1, 0, and have the same general shape. And then if we were to move it 5 units up, we might be even off our scale here, but 1, 2, 3, 4, 5, almost. Okay, we would have function h of x. Now quite clearly, they all have the same vertex. So that means that regardless of whether or not there is a constant that follows the x terms in our quadratic function, which are the first 2 terms, we will be able to determine the vertex of that function quite easily by just partially factoring the first 2 terms. Now when we look at the graph again, question 5 asks us how many x-intercepts does the function have? Well, g of x has 1 x-intercept, the vertex, and h of x has no x-intercepts. So clearly the existence of intercepts, or even the number of x-intercepts, is not important in determining the vertex. The symmetry points can be used to find the axis of symmetry equation, which is the midpoint between any 2 ordered pairs that are directly opposite one another on the function. Okay. So if we were to go back to the Investigate and try to answer the remaining questions, well, we saw that from the graph, g of x had a vertex which was simply the same x coordinate and 2 units higher, as corresponds to the function equation, and then h of x had a vertex which had the same x coordinate and 5 units higher. So in general, we could say that if we were to go to something that resembled more y equals 2x squared plus 4x plus k, where k could be any number, as long as we've factored the first 2 terms, and we know that the symmetry points here are 0 and -2. X equals 0, x equals -2, because both of those would produce, in this case, a 0 value here, and that would leave us with the same y value, meaning they're directly opposite each other. So in that case, x equals 1, -1 rather, the midpoint of those 2 symmetry points would be the x coordinate of the vertex, and the y coordinate would just simply be f of -1. Okay, so these symmetry points are easily determined from the partially factored form, which I've circled in green there. The midpoint between them is the x coordinate, which is the equation of the axis of symmetry. The y coordinate is simply that x value substituted into the function equation in either the original form or the factored form, it wouldn't matter. Okay, so this kind of summarizes the method of partial factoring. And in this case, as k changes, clearly the value of f of -1 would, but we would be able to say that we could calculate it nonetheless. Okay, before I leave this, I just wanted to reinforce the idea that the symmetry points here, although they have ordered pairs, I could list them. Symmetry points would be 0, k, and -2, k. If you're not really sure why it'd be k, just see what happens if you were to substitute 0 in for x. Well, you'd get 0 times 2, which is 0, plus k, which is k. That's this one. If you were to substitute -2 in for x, again, you get -4 multiplied by 0, which is 0, plus k, which is k. So the y-coordinate in both cases is the same, whatever that number is, that final constant term k, it would be that value. Now again, what's more important here is what's the y value of the vertex. So what we really need from the symmetry points is not the y value, but the x values, and those produce the midpoint, which is both the axis of symmetry equation and also it's the x-coordinate of the vertex, which more importantly again is how we find the maximum or minimum value. Okay, the maximum or minimum value, if ever you're asked for it, what it is specifically is the y value. Okay, it's not exactly the x value, although that corresponds, but it's the highest or the lowest vertically, so we're looking for the y value there. Okay, so let's do an overview of the method of partial factoring. This is my preferred method. I like it mechanically. It's very simple and direct. Just involves factoring part of the quadratic function, if there even are three terms, and it really gets into the properties, the symmetry properties of a quadratic function. So this is my recommended choice for students to use even over completing the square. So the whole process is shown before you here. You can fill in the information. You're starting with the function 4x squared, subtract 20x plus 7. The first step is to common factor the terms containing x, and that common factor will be x as well as the coefficient of the ax squared term. So we'll call that ax. Once that's done, you have your function partially factored. The 7, the constant, is always left out of this process. Of course, x would not be common to ever a constant. And then you're going to write the coordinates of 2 points that are equidistant from the axis of symmetry. Those, of course, will be the symmetry points. The points will always be 0, will always be one of them, and then we can call it C. And the other one will be negative b over a and c. Now where are these coming from? Well, remember in the standard form, the 4 would be the a, the negative 20 would be the b, and the 7 would be the c. So when we common factor, we're going to pull out a, and so this number here, which is negative 5, is the value negative 20 divided by 4, which we could represent as b over a. And in this case, negative 5 is not one of the symmetry points, but of course positive 5 is. So hence the opposite of b over a. What would be the y-coordinates of the symmetry points? Well, of course, they'll be the number that's left at the end. That's going to be the c. So regardless, it's the x-coordinates that are important. We can state the symmetry points, 0, 7 and 5, 7. The coordinates of the vertex, okay, well, we know one of them. It's not 7, but we know that the x-coordinate would be halfway between 0 and 5. It's the midpoint of those two x values. So it would be, we can say, negative b over 2a. So if the x-coordinate of one of the points is negative b over a, then halfway between that and 0 would be negative b divided by 2a. Now this is very general. Sometimes you can get bogged down in the generalities, so I'll just say halfway between 0 and 5, which is 2.5. Okay, that's shown right here. That's the axis of symmetry equation, x equals 2.5. The y-coordinate, again, this is a function. Just substitute it into the function machine. F of 2.5 gives us negative 18, so 2.5 negative 18 is the vertex, and in this case, this is a upward opening parabola. It has a leading coefficient of positive 4, and so that would be a minimum for the function. So my recommendation is that you memorize this method and understand it and understand why it works, and you'll find it quite successful at determining maximum or minimum. I'm going to do another problem here just to model one additional problem. This one's found on page 32, number 11. It states that the sum of two numbers is 10, and we're trying to determine the maximum product. Okay, so at first it would appear to be something like an x plus y equals 10, and we're trying to determine a product xy, which is the maximum. Okay, so whenever you read the word maximum or minimum in a problem, good chance that you can apply a quadratic function to model it. In this case, if we were trying to determine the product, we're really looking at saying, okay, well, if x plus y is 10, then the second number is 10 subtract x. And so therefore the product, we can call it p of x is the first number multiplied by the second. And there's our function. So our function is 10x subtract x squared, or negative x squared plus 10x. Okay, so that is a quadratic function. Now, if it's a quadratic function, we know it has a maximum because this opens downwards. So everything at this point that we've modeled with the math all mirrors the description of the two numbers. All right, so how would we find that maximum? Well, we could graph it. We go to a graphing calculator and plot that if we wanted. And if we do, I'm going to put in negative Okay, let's put in negative 10x squared plus 10x. Not knowing where the maximum is, we can just simply plot it. Let's try a zoom 6 plot and see what we can tell from the graph. Okay, so it's fairly close to the origin. Let's zoom in a little bit more. I'll go to the zoom 4, zoom decimal option. And we're even closer still. So in this case, we can use the graphing calculator to search for a maximum. I'll demonstrate it now. You're going to go to second trace. So trace would move along the curve. Second trace searches for specific values, x-intercepts, minimum, maximum is what we want to find here. So we're going to choose option number 4. There's only 3 things we need to provide. A left boundary to the maximum. So I'll go close to the maximum on the left side, the right boundary close on the right side, and then I guess going as close as I can to it. Now this is just helping the graphing calculator search a little bit close to the location of that in case there were other maximum or minimum locally on the graph. We could find the coordinates of one specific. So in this case there's just the one maximum and its coordinates are negative or positive 0.5 for x and 2.5 for y. So that's just a technological solution. Let's go back to the algebraic solution here, which would have us graphing, or rather factoring, okay, the negative 1, which is the a value, out of both terms, so as well as x, and we get x subtract 10. Now just be careful with your arithmetic here. If you distribute that back out, you should be able to produce your original 2 terms. So now, from here, the symmetry points are going to be well, the k value here is 0. So the symmetry points are just 0, 0, and 10, 0. Those would be the 2 values that would make p of x equal. Okay, which means that they're equidistant from the axis of symmetry. Now the axis of symmetry must be midway between them, so the axis of symmetry is our next step, which would be x equals 5. Okay, x equals 5, so therefore the maximum in this case would be at f of 5, which here we can calculate. So the remainder of the solution is just stating the maximum and then going back and stating the 2 values which would give that maximum product, 5 and 5. Okay, here's an overview of the assigned work for the 3 days that we will spend on section 3. I've selected specific questions that complement the video lessons. So all of day 1 is partial factoring, day 2 is completing the square. So for tomorrow coming in, you're reading those examples 2 and 4, self-assess 2 and 3, and then I want you to try all of number 3, which is the mechanics, and then 2 of the problems listed, 7 or 8, 9 or 10. Day 2 will continue on with completing the square. More practice will add in 5 or 6. We'll start on the feedback question number 12. Day 3 will derive the quadratic formula using the method of completing the square, and then we will submit number 12 for feedback. See you in class.